Hello everyone. Welcome to the second lecture in the topic of mathematical logic. In this lecture we are going to discuss about the fundamentals, principles of predicate logic, which is an extension to the propositional logic. You may remember that in the previous lecture we have discussed about propositional logic or zeroth order logic, which deals with the attributes having Boolean or truth values, and we also have seen some of the deduction principles that are primarily applied to deduce certain outcomes and argue automatically or reason about a particular argument automatically. However, if you remember correctly, we have discussed at the end of the previous lecture that propositional logic has certain limitations or insufficiency in expressing some of the concepts and some of the arguments it cannot be able to express. Let us start from where we left the last lecture. If you remember that there are certain arguments that could not be well represented using propositional logic due to the fact that we could not have certain kind of quantifications allowed in propositional logic like some, none, all, every kind of that. So for an example, you can see that if I want to encode wherever Ankush goes, so does the pet dog. Ankush goes to school, so the dog goes to school. Now, the underlying part here, wherever Ankush goes, is not directly modeled using propositional logic because propositional logic deals with simple statements. For example, Ankush goes to school, this thing can be modeled using proposition maybe P. However, if I want to say something goes to anywhere, so these are not part of some constructs that are defined in propositional logic. Secondly, there are certain associations with it because when I say wherever Ankush goes, it means that Ankush can go to a set of places. Now, those set of places could be infinite as well. Now, each of them, if we try to make a propositions out of it, so it will be inefficient and as well as insufficient to express. Similarly, there are constructs like no contractors, some engineers, so these kind of facts we cannot express. However, if you look very minutely, there are certain sentences here also we can express using propositional logic, but not everything that is mentioned here. So therefore, we found in the previous lecture that there are certain insufficiency in propositional logic in terms of quantifications, which may be denoted as some, no one or none, every, and in terms of associations in a true generic sense, meaning that someone can go to some other places, someone can travel in a first class. So these sets of constructs are not defined in propositional logic. So we need a little bit higher order logic, which is called the first order logic or predicate logic. Let us try to dig down that what are the constructs that helps us to express such kind of behaviors in predicate logic. Let us take the first example. Wherever Ankush goes, so does the pet dog. Ankush goes to school, so the dog goes to school. Now, if we try to find out the fundamental constructs that are allowed in propositional logic, first of all, when I am thinking of modeling something which is not personified, that Ankush can go to any place, that's why I need variables. So variables will indicate that Ankush can go to X, Ankush can go to some position Y. So these are unique identifiers which can mimic a set of locations where Ankush can go. Similarly, we can find here that Ankush, dog, these are my constants in this particular argument. So we need constants to express those. Additionally, there may be some non-Boolean functional constructs that we may need. We may say that the age of a person. So therefore, age of a person will return a particular value which is not true or false or Boolean. Therefore, we need certain kind of functional symbols to express these things. The particular example that I have projected here may not contain these functional symbols, but as we go along with our slides and our presentation, we can easily find out such kind of symbols are taking place. Now, as the name suggests, it's a predicate logic, so obviously the core of this logic comes with the predicate symbols. So these predicate symbols are a Boolean symbols which can provide true or false outcomes. And these are very essential to express the core associations between the unknown or the variable parts. So for example, here when we say that Ankush goes, so I need certain kind of predicate to say that whether X goes to Y. And then I will try to code like Ankush goes to school. So therefore, I have generic templates which we call as predicates, which says that goes XY, meaning that X goes to place Y. Please remember that such predicates can have true or false value. If X goes to place Y is true, then the predicate returns true. Otherwise, the predicate returns false. As usual for the propositional logic, we also inherit this kind of connectors, which is negation, conjunction, disjunction, implication, and its extension, which we call as if and only if. So these are similar as we have discussed in propositional logic. Now the most two important aspects, which we call as quantifiers. As you can see that I need to model something as wherever, that is everywhere that Ankush go. Or if you remember the earlier example, there is no contractors, some engineers. So therefore, I need to distinguish between some and for all. So I introduced in the predicate logic, we have introduced two new quantifiers which can help us to express the intent of the statement using there exists and universal quantifier, which is for all. So it is abbreviated as for all and denoted as upside down A, and this is a mirror image of E backwards, which we call as there exist. So with these sets of variables, constants, functional symbols, predicates, propositional connectors, as well as quantifiers, we will show that all of these are helpful to express any such kind of a statement that we fail to code in propositional logic. Now let us come directly to the example and try to code this using the constructs that has just been defined. Wherever Ankush goes, so does the pet dog. Ankush goes to school, so the dog goes to school. So therefore, I want here two kind of a variable that some person is going to some place. That's why I need two variables here to declare. There are certain constants like Ankush, dog, school. The predicate that I need, as I already given an example in the previous slide, that X goes to Y is one of the predicate that I need to encode. Now let us start encoding one by one. We can see there are two formulas or sentences and it will imply one goal formula. So the first sentence says that wherever Ankush goes, so does the pet dog. So I need to first model that Ankush goes to place X. So pet dog also goes to place X. And since it has been said that wherever, so every place where Ankush goes, the dog also goes. So I give for all X. So I quantify this whole formula that Ankush goes to place X imply, that is, if Ankush goes to place X, then the dog also go to place X. But this happens for every X positions or places wherever Ankush can go. So I bound it using a quantifier called for all X. Wherever Ankush goes, if Ankush goes to X, then dog also goes to X. So it expresses that wherever Ankush goes, the dog follows. The second is a bit straightforward, which is Ankush goes to school. So we have a predicate called goes. Now Ankush goes to school, we can model it as goes Ankush school because it says X goes to Y. Now our goal is to find out that the dog goes to school or not. So similarly, we can use goes dog comma school and say that this predicate mentions the state or encodes the statement the dog goes to school. Now this is as part of the representation of the predicates or the predicate logics that we are discussing. So we formulate the arguments in English in terms of a logical construct using the defined variables, constants, predicates and certain connectors and as well as for all quantifier. Now what we are interested in is to find out a deduction system or a deduction rules which can say F1 and F2 imply that my goal, this formula is valid. So all of these we have already done in propositional logic, but after we are conversant with the formulations and representation in predicate logic, we will see how the deduction rules can follow that this statement is valid. So we will introduce certain deduction rules and through which we can also build up a process or system and reason about these predicate logic constructs. Let us go to our example 2. No contractors are dependable. This is I should encode this as formula 1. Some engineers are contractors. Therefore, some engineers are not dependable. Here you see one thing, that I need to define universally that a person is a contractor or not, a person is a dependable or not, a person is an engineer or not. And here, unlike the previous example, there are no constants like Ankush or dog. So our predicates here would be to define that contractor X denotes X is a contractor. Remember that if this is a predicate, that means it will output a value true if indeed X is a contractor. Otherwise it will return false. So I have predicates like dependable X and I can also have predicates like engineer X. Respectively they define X is dependable and X is an engineer. Now look at the first statement. No contractors are dependable. Therefore, I can code the first statement F1 as that, let's say X is a contractor, imply X is not dependable. So if X is a contractor, then X is not dependable, and my statement says that none of them is of that type. So no contractors are dependable. So if you think it clearly, you will figure out it says that all contractors are not dependable. So therefore I can say that for all X, if X is a contractor, then X is not dependable. And it happens for every X. So no contractor is dependable. In an alternative sense, you could also see this statement as that since I say that all contractors are not dependable, it means that there should not be any contractor who is dependable. I will not get such a person. So therefore, alternatively, I can say that if X is a contractor and X is also dependable, such an X cannot exist. So if I say there exists X, such a thing will not happen. That's why I wrote it as not there exists X or any person who is a contractor as well as he is also dependable. So these two statements mean the same thing. And as the course of the slides or the lecture we proceed, we will try to show you how these two are getting equivalent. But as per the intent in the English, we can easily figure out that both of them means the same. Let us come to second statement. It says that some engineers are contractors. Therefore, I can encode it that there is engineer, suppose X is an engineer and X is also contractor. So it says some of them happens to be like that. So therefore there exists X who is an engineer as well as a contractor. So remember that there exists means that there is an existence of at least one such case. Since we say some, therefore it may be one or it may be more than one, but this statement suggests that there exists someone who is engineer as well as contractors. Now you may be tempted to think that why in the previous case I encoded it using an implication, here I used an AND instead. What if I use that there exists X, engineer X imply contractor X? Then the meaning would be that if X is an engineer, then he is a contractor and there exists such a case. So if you try to rethink about this, that what do we mean by an implication? So the overall statement or the overall formula is valid even if no engineers are found, because if engineer X imply contractor X is the case and engineer X fails, then the overall formula becomes valid. However, if you look at the English statement, it says that some engineers are contractors, which inherently mean that there exist some engineers in the group who are also contractors. So I have to eliminate the possibility of not getting an engineer at all from the group. So therefore, putting an implication instead of AND will not serve my purpose alone. So if you look at the alternative now in the gray color, I have done the same thing, that there exists X. If X is an engineer, then he or she is also a contractor. But to eliminate the possibility of no engineers found from the group, I have also conjunct it with there exist at least some engineers in the group. So therefore this F2 and the below line, the alternative of F2, this whole sentence are expressing the similar intent, which is some engineers are contractors. Now finally we get to see that therefore some engineers are not dependable. Going by the same analogy as F2, I can say that if X is an engineer and X is not dependable, there exists some of those combinations, some of those persons which are of those combinations. So therefore I say there exists at least one or more of them, such that X is an engineer as well as X is not dependable. Again, our final goal would be how can we formally deduce whether F1 and F2 imply the goal or not. Let us come to the third example, which says that all actresses are graceful. Anushka is a dancer, Anushka is an actress, therefore some dancers are graceful. So in the similar vein, let us try to find out what are the predicates, what are the constants, and what are the formulas. First of all, you can see that Anushka is a constant, dancer is a constant, actress is a constant. These three are the constants here. Or in other ways, you can also relate that Anushka being a dancer and Anushka being an actress is kind of a profession, or is a professional dancer or a professional actress by using a predicate as well. Now, going by that, we can always say that X is an actress, X is a dancer. We will denote it as actress S, dancer X. And when we say X is graceful, we can also say that X is graceful. So therefore, if we revisit this whole statements, we will find that Anushka is a constant, and these three are predicates which we need to encode these statements, like X is an actress, X is graceful, X is dancer. Now let us try to encode the formula that all actresses are graceful. So the first formula says that if X is an actress, then x is graceful, and it happens for all x. So therefore the formula says for all x, if x is an actress, then x is graceful. Now see here, unlike the previous one, we cannot put here and, because it says that all actresses are graceful, as well as it also says if there are no actress, then I do not claim anything about graceful. So if I put an and here, then if there are no actress in the pool, then this whole statement fails. But I do not want to mention anything, and the world assuming to be true, if there are no actress in the pool, I want this to hold in this universe or world. So therefore, as we have just in the previous case we have discussed, so for all x, if x is an actress, I need x to be graceful. So we encode it in this way. Now as you can see that dancer x is a predicate denoting x is a dancer. So the second statement here says Anushka is a dancer. Therefore I could mention it as dancer Anushka. The third statement says Anushka is an actress. Therefore actress Anushka will be the predicate for it. Now my final goal is to propose that whether some dancers are graceful. So if I encode it in the similar manner, I will try to see whether x is a dancer as well as x is graceful if there exists some x, such x. So there exists x such that dancer x and graceful x. It means that whether some dancers are also graceful or not. Now with these three statements F1 and F2 and F3, our job is to find out whether F1 and F2 and F3 implies G or not. We will see how we could deduce this as valid or invalid in couple of slides after some time. Finally, a little bit complicated example that we have is every passenger either travels in a first class or in second class. Each passenger is in second class if and only if he or she is not wealthy. Some passengers are wealthy, not all passengers are wealthy. Therefore, some passengers travel in second class. If you look at carefully that I need to say that so I need to encode here every passenger. So therefore I need to say that X is a passenger or not. So I need to declare a predicate for passenger whether X is a passenger or not. I need to declare a predicate for someone traveling in first class as well as someone traveling in second class. I need to declare a predicate here for someone is wealthy or not. So with that information gleaned out from the statements in the arguments, let us try to form predicate over a variable x universally. So I say pass x is to mention that x is a passenger. I say FRST x is to mention that x travels in first class. Similarly, SCND x to mention x travels in second class. And WLTY to indicate x is wealthy. Now these four are my basic predicates through which I will try to encode each and every sentence. So the first sentence says every passenger either travels in first class or in second class. Look here that either or, because a passenger cannot travel in both class simultaneously. Therefore, if you try to look at this, you will be tempted to think about this, that passenger X, if X is a passenger, then he travels in first class or in second class, and it happens for every passenger. So for all X, if X is a passenger, he travels either in first class or second class. But if you minutely look, due to the inherent exclusive or nature of traveling in either in first class or in second class, the better argument representation for the statement 1 could be that for all X, if X is a passenger, then he travels in first class and not in second class. or in second class but not in first class. So this is the exclusive or thing we have incorporated, whereas previously in gray, where we are trying to incorporate only an or without considering the fact that a passenger cannot travel in both places. So second is more apt to represent the first statement. So it says that for every passenger, that is for all x, now x is a variable which indicates if x means that x is a passenger. So for all x, if x is a passenger, then x travels in first class or x travels in second class, but not in both. The second statement says each passenger is in second class if and only if he or she is not wealthy. So I need to encode here that each passenger is in second class. So for all passengers, I need to encode that for every passenger, it will imply that he or she will be in second class if and only if he or she is not wealthy. So let us try to first model the right side part of it, that someone travels in second class if and only if that person is not wealthy. So which is mentioned as here that second x, that means x travels in second class, which imply that x is not wealthy. And since it has an if and only if, so the other part is also there, that if x is not wealthy, then x travels in second class. So these two, with a conjunction or and together, mentions the fact that a person x travels in second class if and only if he or she is not wealthy. Now the whole statement says that each passenger is in such condition. So if I try to complete this statement using arguments or predicates, I will say if x is a passenger, then this thing will happen. So if x is a passenger, then he or she might travel in second class if and only if he or she is not wealthy. So for all passenger, that is for all x, if x is a passenger, then the right side thing that we discussed will be true. So each passenger is in second class if and only if he or she is not wealthy. The third condition says that some passengers are wealthy. We have already seen how to encode such thing in previous two examples. So if x is a passenger, then x is also wealthy. So there exists some passengers, that is there exists x such that passenger x and wealthy x. There is some passenger who is also wealthy. Not all passengers are wealthy. So F4 says, first of all, if you try to quote that all passengers are wealthy and negate it, it will have this same intent. So for all x, we say that if x is a passenger, then x is wealthy. And we put a not before that. It means that for all passengers, they are not wealthy. So all passengers are not wealthy, which is the case that all passengers are wealthy. Put a negation before it. Or alternatively, you could think of this statement as not all passengers are wealthy means that there exists some passenger who is unwealthy, not wealthy. So therefore, I can also say that there exists some x who is a passenger and that person is not wealthy. So these two again are of similar intent or expresses the similar intent. Now finally, my goal is to show whether some passengers travel in second class given all these previous statements holds. So I encode it as there exists some passenger x, that x is a passenger and x travels in second class. One point to note here is that when you say there exists x, it does not implicitly says that for all passengers. To denote for all passengers, you need to associate x with certain predicates to make sure that you say that what x you have taken is of passenger, denoting that x is of a passenger. Only indicating for all x, and if you try to say that for all x sc and dx, it means that X travels in second class. It does not also mean that X is a passenger, because X is a variable which can have associations with respect to any of the predicates. So therefore, if you have to quote that there are some passengers who travels in second class, so X is a passenger, X travel in second class, both of the things should be present. So finally, again for this case also, our goal is to say whether the first four formula or the statements imply the goal or not. With this background, we found that the most important constructs that we have introduced here are primarily predicates, as well as there are certain constructs called the quantifiers, that is existential to indicate everyone for all, and universal to indicate everyone or for all, and existential to indicate there exists or some. So with respect to that, we could also find some interesting observations over the quantifier where we could use a nesting of a set of quantifiers. So let us take some examples. Our first example says everyone likes everyone. So therefore, if I have a predicate likes xy to denote that x likes y, therefore I am trying to say every person likes every person. So I would say that if x likes y and it happens for all x, for all y, I say that for all x, for all y likes xy, which means that everyone likes every other one. Here you could also have put a bracket after for all x, that is in between both for alls, and ended it after like. It does not change the intent or the meaning of this. What it tries to only say that everyone, that is a variable which you try to denote that x, likes everyone which is denoted by the variable y. Here, according to the intent, it also says that if everyone likes everyone, then there is a particular person who likes himself or herself too. Because I say for all x in this group likes for all y in that group. So that's why everyone likes everyone is encoded in this way. Someone likes someone. So therefore I can say that again likes xy means x like y. So there exists some x and there exists some y where x likes y. Here you may, if you try to think deeper, you will see that this y may be the same x as well, or maybe a different one, because I only mentioned that someone likes someone. I do not mention that someone like himself or herself. I have not mentioned whether someone like some other person. I say that someone from that group likes someone. So therefore, there exists someone in this group and there exists someone in that group also, where I can say that the first one likes the second one. That's what I want to mean by this intent. The third property here says that everyone likes someone. So it means that for all x, there exists some person whom x likes. So for all x, there exists a y such that x likes y. So for all members in the set, there exists someone whom x likes. But that particular person may not be unique for everyone. Please try to understand this fact that everyone likes someone means that in the set of everyone there may be person A, person B, person C. A may like someone P, B may like someone Q, C may like someone P. So therefore, for every person, there exists some person means at least there is someone whom X can like, but that person may not be the same. Someone likes everyone. It means that there is someone in the group who likes every person in that group. So there exists X, for all Y, X likes Y. So there may be multiple persons in this group which loves everyone, but at least one, if it is there, we can say that there exists X for all Y such that X likes Y. Now let us try to see. So these all are in active voice as per the English statements are concerned. Let us try to tweak it down and say in the passive voice. If we try to see the passive voice of the first statement, example A, then we get that everyone is liked by everyone. See, here I am saying that for all X, for all Y, so every person X here likes every other person Y. Here I want to say that every other person, that is everyone, is liked by someone. So for every person in the set, there is every other person who likes that person. Look at the difference between the first example A and example I here in both places, the exchange in the position of quantifiers due to the nature of active statement and passive voice statement. Similarly, the second one says someone is liked by someone. That means, as in the previous time we encoded it using this way, this time also we exchange the position of the quantifier by saying that there exists someone who likes that person. There exists someone in a set who is liked by there exists someone from the first set. The most interesting observation is observation 3 and observation 4, these two examples, where we say that someone is liked by everyone, which means that there exists some person who is liked by everyone. So there exists Y, at least one person or maybe more, but there exists Y who is liked by everyone. So X likes Y. There exists a Y whom everyone likes. Now look at the active voice once again. When we say everyone likes someone, that means, as I already explained, that everyone is liking someone. That someone may not be the same for everyone. So A likes P, B may like Q, C may like again P, D may like R, such a way. However, the passive voice of the same intent says that there exists a person whom is liked by everyone. Here, this person is unique for everyone. So if this person is P, then P is liked by A, P is liked by B, P is liked by C, and so on. Similarly, if you have understood this change in the logical formulation of active and passive voice, the last statement is in similar vein. When we say someone likes everyone, we code it using this way. Now the passive voice says everyone is liked by someone. So for all Y, everyone, there exists an X where when X likes Y. Again, if you try to think carefully, you will find that these two statements are not logically implying the same thing. Here it says that someone is there who likes everyone. That means there exists some person here who likes every other person. So that person is fixed. At least one such case happens. Whereas it says that everyone is liked by someone, which means that for all Y, there exists some person when that person likes Y. So, the last two statements, if you consider minutely, you can easily see that if there are different quantifications like for all and then interleaved with there exist, it is not straightforward if we interchange the position. Logically, the meaning does not remain the same. Whereas, if we interchange the positions of similar quantifiers, it's nesting in such a way that the variable is participated within that quantifier. So for the example A and example I could find that the intent logically remains the same. So we could conclude by these examples that active and passive voice statements in English are not logically similar, because if there is an involvement of quantification and which is of different type, then the positional change of the quantification makes the intent different. I reiterate that everyone likes someone means that for everyone there is someone, that someone may differ. Whereas here someone is liked by everyone means for a particular person, everyone, that person is liked by everyone, so that person does not change here. Little bit complicated examples with the same form predicate, that if everyone likes everyone, then someone likes everyone. So if everyone likes everyone is encoded as this, that for all x, for all y, x likes y, then, which is implication, if this happens, imply this, someone likes everyone, so there exists x, someone, for all y, likes xy. Looking at the English statement, you can easily conclude that this is a tautology, right? Because if everyone likes everyone, then there obviously the case that someone likes everyone must be true. However, looking at this formulation, just to give you an intuitive idea how do we deduce that when we see there exists x, that means that to have this side to be true, I need to ensure certain valuations, or I need to choose a valuation because it says some x satisfies this. So let's say x equal to a satisfies this. So if I replace it here, this statement will become for all y likes ay. Now the case is that since for all x this is true, therefore for any x here, if x is a also, this inside statement with x replaced to a is true. Now we can figure out both of them become similar. So therefore, if for all x this is the case, then it must be that there exists this is the case. So this is an intuitive notion, so we will see the deduction rules how we can go by and prove this more formally. The second statement says, if some person is liked by everyone, then that person likes himself or herself. So if some person is liked by everyone, then that person likes. So some person is, let's say there exists y, that person is liked by everyone. So for all x, x likes y. So x likes that person y. Then that person also likes himself or herself. So I can say y likes y. So therefore see, there exists y likes yy encodes the right side. And there exists y for all x likes xy encode this left part. If some person is liked by everyone. So I can take out there exists y because that quantification is in the beginning of both of the parts. So I can take it out and say that there exists y for all x like xy implies likes yy. So with this intuitions over the examples on the quantifiers for all and there exist, we could also introduce certain notions over the quantifiers. For example, we could say that what do we mean by contrapositive of this? Essentially, when we studied propositional logic, we have seen that if A implies B, then if not B happens, then it automatically implies not A. So that is what do we mean or define contrapositive to be. So here, for all x, if px is true, then qx is true, where px and qx are predicates having truth values, Boolean values. So the contrapositive of this particular formula would be for all x, not of qx, imply not of px. So whenever q is not true, then formula p over x is also not true. we define converse of the same formula as just saying that the effect would be my cause now and the cause would be my effect now. So it says if Px happens, then Qx happens. I will say the reverse thing by saying that if Qx happens, then Px happens. Remember, unlike the first case, the contrapositive nature of the formula, this formula remains equivalent. The second case, we are not talking about equivalence here. So those two formulas are not logically equivalent anymore. However, we define converse of a formula by implication formula by this way. Similarly, the inverse of a formula is saying the negation to happen and the outcome is also the negation is happening. So for all x, if Px imply Qx, the inverse I will define as for all x, not Px will imply not of Qx. Sometimes what we need is that if we can encode a formula in true sense, sometimes there is a need to encode it using its inverse, using it and its converse form. And in natural deduction or deduction by rules using predicate logic, these formulas come in handy sometimes. Most importantly, there are very interesting negation law of quantifiers which follows indirectly from the De Morgan's principle. Let us try to find the intent of it. So what do we mean by for all x Px? It says that for all x, x satisfied P. Suppose P denotes passenger x. So it means for all x, x is a passenger. So what is the negation of this? That I want to denote here not every passenger. So that means there exists some x for which x is not denoted as passenger, which is the right side. There exists someone who is not a passenger. So these two intuitively in logical sense are equivalent. So equivalence, we write it using 3 horizontal parallel bars or a thick arrow in both sides as well. Similarly, if you try to reason about the second formula, I say that without negation, this formula says that there exists x where Px is true. If I say not of that, so it means that at least one such case will not happen. So that means for all such x's, Px will be a failure, which is the right side, that for all x, not of Px to be true. So again, if you try to take the analogy of passenger, we can say that for all there exists x, x is a passenger. If it is not the case, that means that no one is a passenger, so which can be encoded as everyone is not a passenger, which is the right side. Here you can easily figure out that x, for all x means every element belonging to a particular class or set or a group. There exists means there is some elements, at least one, that belongs to a particular class or set or a group. Now intuitively you can think it of for all x as, let's say x0, x1, x2 are the members of that particular group. Then for all x denotes the conjunction of all, that I want to reason about with every element here. Whereas there exists x indicates the disjunction, that I want to reason about at least one. More than one is okay, but at least one I need. So now if you try to think about these formulas, do not replace these formulas by and or, because both are applied in different contexts. So if you try to reason about or think of these formula as and or, you will easily see how De Morgan's principle get implied here. So this is for an intuitive understanding, I have mentioned this. Now let us see that what this brings us to. Let us go back to our example where we are arguing about this implications and ands. Now you try to read about this formula that not all passengers are wealthy. One of the way we tried to encode it is that for all passengers are wealthy and negate that. The other way we tried to encode is that some passengers are not wealthy and there exists some of them. So see, if you try to push this negation inside as per the negation law, it will become, for all will become there exist, and this negation will push in. Now this implication, as I have shown in the while you are studying propositional logic, that A implies B means A or not B. So the negation will come in and De Morgan's law will be applied, and you will see just the similar alternative formula that is written here in green. So these two formulas are equivalent, and as we can also find out from the intuitive meaning of the English statement. Finally, let us try to see that we have introduced something called function symbols, and I have given an example like age x, which says the age of x, which is not a Boolean predicate, which answers certain values or certain elements as an output, and it gives the age of the x. So how can we use that to encode the predicate logic formulas? So first of all, according to our colloquial knowledge, let us try to encode this one, which does not involve any functional symbols, but gradually we will enhance this formula so that it includes the functional symbols. If x is greater than y and y is greater than z, then x is greater than z. So this should be z instead of x. This is a mistake. This should be z. So here it is obvious from a mathematical sense, and it is known to us, because we are saying that x is greater than y. We are saying y is greater than z. Then obviously x should be greater than z. But how do we encode using predicate logic? So here we need only one association of predicate called greater than. So we call it as GT, indicating x is greater than y. So the first thing, x is greater than y, is our GT x comma y. Then y is greater than z is our GT y comma z. So if both of them happens, this will imply that x is greater than z as well. So this is true for every x, for every y, and for every z which satisfies this thing. So we bound it as for all x, for all y, for all z. Whenever x greater than y and y greater than z, I will obviously get x greater than z. Now let us try to introduce the functional symbols. The age of a person is greater than the age of his or her child. Here obviously we need to denote something called age of a person or age of x. So therefore I say age of a person x as age x. This is a particular function symbol which returns a value instead of a Boolean answer, as we saw in the predicate called greater than. Because if x is greater than y, it will return true. If x is not greater than y, then it will return false. Whereas age x will return me a number in this case. Also we need a predicate called child x comma y, which to denote that x is a child of y. Now I want to say here is that the age of a person is greater than the age of his or her child. So I will say that first of all, this will happen for every person and his or her child. So therefore, for every child of a person, so for every x, for every y, where I denote that x is a child of y, which will imply that age of y is greater than the age of x. Age of the person is greater than the age of the child. So the right side of the implication shows a predicate which takes two functional symbols, which is age of y and age of x. Just try to relook at the predicate GT. So it says that x is greater than y, where obviously x and y are my placeholder variables, but x and y will take some value. Here functional symbol by age x and age y, I am supplying those values into it. So it is interesting to note that predicate not only takes as arguments only the variables, but also as functional symbols which have non-Boolean or a particular value to it. So this statement encodes that x is a child of y imply that age of y is obviously greater than the age of x, and it happens for every child person and his or her child pair. So for all x and for all y this happens. The age of a person is greater than the age of his or her grandchild. Now you can already get a sense that since I can say the age of a person is greater than the age of his or her child, so obviously I can also say child of child is my grandchild. So I can say that x is a child of y and y is a child of z. These two together informs me about that x is a child of z. So when that is the case, again I will do the same thing as I have done in the right side, that the age of a person is greater than his grandchild. So if x is a grandchild of z, then age of z will be greater than the age of x. And this will happen for every child x who is child of y, and for every child y who is child of z, which satisfies this formula, that is x is a grandchild of z. If you think also that if I want to introduce a new predicate called grandchild x comma z, that is also possible, then this particular statement will be grandchild x comma z imply this one, and there will be two variables x and z here, and which will identically look just like the formula before. Okay, so you can also do that, but I have used the same predicate without introducing a new predicate to encode this one. Finally, a little complicated one is that the sum of ages of two children are never more than or equal to the sum of ages of their parents. So here I want to ensure that the sum of the ages of the parents is obviously more than if I sum up the age of two children. So here I want to introduce another new function symbol, sum xy, to just denote x plus y. So this is a functional symbol which says that which will return the value of x plus y. So let us try to encode it by first encoding that two children of a parent. So we can say that w is a child of y, w is a child of z. These two together make sure that w has parents y and z. Again, I can say that x is a child of y and x is a child of z. These two make sure that x is also a child of y and z. Here, these four together therefore mentions me that w and x are both childs of y and z. So y and z are the parents of w and x. So I got two children, I got both the parents. wx are my two children variable, yz are my parent variable. This will imply that the sum of ages of yz must be greater than the sum of the ages of w and x. So in the right side of the implication, I have a predicate greater which takes two particular value as arguments, which is basically the sum of y plus z, which are the parent age sum, and the sum of w plus x, which is the sum of the ages of the child. So obviously the parent's age is more than the child. Now this will happen for every child and for every parent. So for all w, for all x, for all y, for all z, this will happen. Just one point to note here, I have not introduced this thing inside the formula, that when I say w is a child of y and w is a child of z, the only thing I do not consider here that y and z could be same person. Therefore, it may not be the case that I encode this whole thing properly as parents. So, however, if y be the same person too, then also the sum of the ages will definitely be more than the sum of the age of the child if the child age is less than the parent age. But it is better to also write a particular proposition and end it with the whole thing that y not equal to z, which means that both parents, the father and the mother, I am not taking the same person as the parent of the child. So this thing I missed here, but to complete this one, you can just end with all this that y not equal to z. So by this set of examples, we have shown that how we could use function symbols, how we could use predicates, how we could use the variables and the constants, and how we could nest it inside the predicates, all the function symbols or the variables, and how we could encode and try to figure out the quantification and try to nest it up. In the next lecture, we will try to more formally see the syntax and semantics of these kinds of constructs, and we will try to figure out how to deduce a certain goal or outcome from the basic premises that is given to us. So we will discuss in details all this with suitable examples in the next lecture. Thank you.